Acid concentration and acid strength is a tricky concept for Chem 20 folks to get their brains around sometimes. I'm going to try to make it as simple as I possibly can. We talked about concentration before, and we said that concentration was how much solute you have in a solution. So if I take 1 mole of, I don't know, sodium chloride, table salt, and I dissolve it in 1 liter of water, boom, I have a solution of concentration 1 mole per liter. If I take 1 mole and I dissolve it in 2 liters, then I have 1 divided by 2, a concentration of 0.5 moles per liter, etc., etc. You literally just find your moles number and you divide by your liters number, and that gives you a molar concentration. Great. So in an acid, it's literally the same. It's how much acid you put in the water. So if I measure out 1 mole of, I don't know, HCl, and I put it in 1 liter of water, guess what? The concentration of HCl is 1 mole per liter. If I take 1 mole of, I don't know, maybe we talk about acetic acid, the stuff that makes vinegar. If I take 1 mole of acetic acid and I dissolve it in 1 liter of water, then the concentration of the acid is 1 mole per liter. How much acid I put in the water compared to how much solution there is. Absolutely simple. Nothing weird about this. Here's where it gets a little bit goofy. Strength and concentration don't really have anything to do with each other. Strength of an acid is how many H3Os you make. What do I mean by that? Well, some acids we call strong acids. And in a strong acid, all of the acid breaks apart and turns into H3O+. What do I mean by that? I'm going to do a little crummy drawing. All of my acids are just going to be called HA. So I'm going to do maybe, I don't know, let's do 5. There's 3 acid molecules. There's 4 acid molecules. And there's 5. So in a strong acid, all of these are going to ionize. And when they ionize, of course, they turn into H+ ions. And they also turn into whatever is left. And in this case, considering we're just using A as our counter ion, we're just going to call them A-minuses. And that means that all of these, and I'm not going to do all of them separately, they're all going to hook up with water and form hydronium ions. And so that means you have a lot of H3O ions. Actually 100%. So that means that if I have 1 mole per liter of HCl, that's going to translate into 1 mole per liter of H3O. in a strong acid, the acid concentration is the same as the H3O concentration. So there are three big boy acids that do this that we talk about. There's a couple more in reality, but the big three are the following. HCl's one of them for sure. Then we have nitric acid. Again, remember that means if I make a 1 mole per liter nitric acid solution, that means that I am getting a 1 mole per liter hydronium solution. And the last one is sulfuric, which is H2SO4. Oh, that's a really bad 4. There we go. So that's also going to form a 1 mole per liter H3O. So again, 100% of the acid that you dissolve turns into H3O and whatever the counter ion is. That's a strong acid. Now, you can probably guess only some of the acid in a weak acid turns into H3O+. So what does that mean for us? I'm going to do a weak acid now. I'm not going to draw all of this. But only a couple of these are going to turn into H3Os. So some of these are just going to stay not broken apart. And only a couple of them will ionize. So the big difference, look at these acid molecules compared to what's going on up here. In a strong acid, they all ionized, and all of them made H3O. In a weak acid, only some of them ionize, these two, but 3 of them remained not ionized. So they remained together. What does that mean for a weak acid? It means that, let's say we have a 1 mole per liter of acetic acid. We're going to get like 0.04 moles per liter of hydronium. So it means that the amount of hydronium that you make in a weak acid is far, far lower. So if you had a choice, and I would never make you do this choice even if we were in person right now, if you had a choice between dipping your hand in 1 mole per liter nitric acid versus 1 mole per liter acetic acid, think about that. Both of the acid concentrations are the same. They're both 1 mole per liter. Which one would you rather dip your hand into if you had to? The choice is clear. You would rather put your hand in the acetic acid because it is breaking up into far less H3O. It's giving you less acidity. That means that the pH of a weak acid is not very low. The pH of a strong acid is around 1 to 2. So strength of acid is how much H3O you can make. Concentration of acid is how much acid is actually in your solution. Another way of doing this that I'll show you is by writing a dissociation equation or an ionization equation. Pardon me, which we've done before. So for a strong acid, like HCl, (100% of our HCl turns into these. And of course, all of your H pluses are then going to go and find an H2O and form hydronium. Great. But if we have something like, I'm going to do oxalic acid. And I know this is like a really hilarious formula. A lot of people are like, yo, Lorenz, why don't you do HC2O4? I like to write out oxalic acid, which is a weak acid. Oxalic. I like to write it out, and most scientists like to write it out like this, because it shows you which H is the guy that's going to fall off. It's going to be it's going to be an H on the end, either the start or the beginning. I'll show you another weak acid in a second. A lot of these acids, instead of having a single ion or a single atom as their counter, they've got a big carbon-containing molecule, or a bigger carbon-containing molecule. So yeah, this is going to make H pluses. That's not surprising. And it is also going to make HOO, CCOO minus. That ion is called the oxalate ion, and I believe it is in your data book as well. But does this happen 100% of the time? Not even close. Way less than 100% of the time. That's what classifies a weak acid. Here's another weak acid, CH3COOH. And actually, I'm going to draw this guy as well. Here's my CH3, C double bond O, OH. This molecule is acetic acid. This is the stuff that makes vinegar. And when it is added to water, it's going to make H pluses. Pardon me. And it's going to make the leftover, the counter ion, which is CH3 COO minus. Oh, I keep doing the same mistake. That's really awkward. CH3 C double bond O with a minus charge. And that's aqueous. So what's going on in molecule land? What does this guy look like? Well, actually kind of interesting. So obviously we have our H plus, and then we have this guy right here, there's now a minus charge there. Just for the record, this structure here can undergo resonance, meaning that the minus charge can pop up here and the double bond can pop down here. That stabilizes the ion. And since this is a weak acid, we draw less than 100%. So that means that if I make a 1 mole per liter solution of acetic acid, the amount of H plus and by extension the amount of H3O is way, way, way less. So, yep, if you have to make the decision, 1 mole per liter strong acid or 1 mole per liter weak acid on your face or dipping your hands in or whatever, you're going to always choose the weak acid because it makes a lot less H plus.